Right, good morning. See, students, today I will explain electrostatics. Electrostatics. So, electron means electron, and statics means rest. Electron at rest. The study of electron at rest. The subject is known as electrostatics. Now, in this lesson, we mainly focus on calculating the electric field, electric force, electric potential energy, and capacitance. So to calculate the electric field, but here electron is the charge. That's why, and we will consider a isolated charge. Isolated charge. This isolated charge, let it there is some electric field lines will be radiating around it. Right now, let at a distance r from this charge, there is a test charge is kept in the region of electric field, which is at a distance r. Now, there is a force of attraction or repulsion between the two charges is equal to some constant times product of the two charges q naught by r square. This is according to Coulomb's we define. Electric force is directly proportional to the product of the charges, inversely proportional to square of the distance, is equal to some constant times. That constant is called 1 by 4 pi epsilon naught. Epsilon is equal to permittivity of free space. Its value is 8.85 into 10 power of minus 12 Coulomb square by Newton meter square. That is its SI unit. Now, electric field also. What is electric field? How can we calculate the electric field? By the definition of the electric field, it is the electric lines of force. It is defined as electric lines of force per unit test charge. So already we know electrostatic force. Therefore, electric field is defined as both are vector quantities. That's why we are represented with a bar. Okay. Here also as a vector quantity we can represent k q naught by r bar square into r cap. So here we mostly using the only magnitudes quantities. So F known as k q naught by r square into q naught. Q naught cancel. Therefore, the magnitude of electric field can be written as kq by r square. So this is the formula for electric field. This is the formula for electric force. For the both, the source is charge. Right? That charge is here in this lesson. We are considered it as at rest. So about the charge, there is a fundamental. All of you know it is a fundamental charged particle, neither created nor destroyed. This charge is in the form of always quantization, means integer multiples of electron. This charge will be produced by conduction, induction, and by the friction. Now, similarly, what is electric potential? This also electric potential also defined as work done per unit charge. So, after defining this also we will get the formula. Electric potential is defined as kq by r, and electrical potential energy is minus q naught by r. These are all the very basic formulas regarding this electrical force, electrical field, electric potential, and electrical potential energy of 2-point charges. So this Coulomb's law can be applied for only point charges, point and isolated charge. Okay, and between these 2-point charges only we calculated the electric field and corresponding electric potential and all. So based on this very foundation points, now electric flux. So what is electric flux? Electric flux means whether it is a magnetic flux or electrical flux or any general flux speaking means lines, electric field lines per unit perpendicular to surface area. Electric flux is denoted by phi. Okay, number of electric field lines, number of electric field lines perpendicular to the surface, perpendicular to the surface. So more number of electrical field lines are spreading or radiating perpendicular to the surface means more flux, less number of field lines means less flux. This can be very easily we will understand. Let this is a surface, okay, some shape of the body I considered here, and here there is a area always perpendicular to the surface. Let electrical field will be acting in this direction, and the angle between them is theta. Now the amount of electric flux, okay, electric flux is a scalar quantity. That's why in the direction of the area, this electrical field is we resolving. That's why the component of electrical field along the area is E cos theta into area. That means E also vector, A also vector, as this is a scalar, this is scalar product, so that we can write EA cos theta. If theta is 0 degrees, maximum flux it is 90 degrees, 0 flux means perpendicular to the surface area or along the area maximum flux. If the electrical field lines are radiating along the area, then in that direction we will get maximum flux, and perpendicular to the area, okay, perpendicular to the area means okay, the electrical field which is perpendicular to the area in this direction is, this is E sin theta, this is E cos theta. So this component cannot produce any, cannot responsible for any electric flux. E cos theta component of the electrical field lines only responsible for the electric flux. If theta 0, maximum flux. If this is 90 degrees means in this direction there is no any electric field, electric flux we will get. Now using this electric flux and Gauss law, all of you know, it is a very empirical formula famous. This electric flux is equal to EA, okay, which is equal to some constant, means a charge enclosed by that Gaussian surface to the epsilon naught. This also by the sphere. Considering the sphere, we can obtain this right side, but the total electrical flux means integration, and enclosing the Gaussian surface means circle we are using. That is the meaning of integral of integral of EA is equal to cyclic integral of EA is equal to QE by epsilon naught. QU means enclosed charge. So how can we understand this? And using this we will calculating the electric field for some shaped bodies. Let's suppose this is a infinite wire on which there is a uniform charge is retained on the infinite wire. Okay, how much charge will be contributed here? Let's suppose Q. But I want to calculate the electrical field at a point P which is perpendicular distance from this center of the wire. This thickness is neglected, right? Now, how can I kind of calculate the electrical field lines? Electrical field lines are spreading 360 degrees, okay, around this wire. As wire is infinite, the charge is not finite. Charge cannot be exactly, we cannot calculate it. That's why it is difficult to calculate the electrical field. To overcome that difficulty, this Gauss scientist will demonstrate this formula. This also for symmetrical bodies only we are using. Using this, he constructed a Gaussian surface through this point of P. Now we know the exact amount of the charge, how much enclosed in this Gaussian closed surface. Let this length of the cylindrical surface is L and the radius already R. So from the geometry, cyclic integral of E into what is the Gaussian surface area, 2 pi r, 2 pi r into length. This is a Gaussian surface area is equal to how much charge is enclosed here. Let again known quantity lambda is the linear charge density. So from this we know the charge how much enclosed in this surface means okay, we will calculate from the lambda is equal to charge enclosed by L. Therefore charge enclosed we can calculate lambda L. Here we will substitute here in place of QE lambda L by epsilon naught. LL cancel. Okay, so this is the total surface area, curved surface area we taken. That's why E is equal to lambda by 2 pi epsilon naught R. This is the one of the way we will calculate the electrical field. Okay, so but what are the surfaces? Why we calculate considering the curved surfaces area only? Why not this top surface and bottom surface? Already we know area will be perpendicular to surface here. Electrical field will be in this direction, so that there is no flux contributed here. Similarly, in this surface also area perpendicular to surface, but electrical field lines are here in this direction only. So that's why top surface and bottom surface there is no contribution of the electrical flux. Only curved surface only is responsible for the contribution of electric field. So this is one of the way we will calculating the electric field. And similarly, using this Gauss law or without Gauss law also, for uniform charge distributed, simple integration and differentiation methods, we will calculating the electric field. For example, this is a non-conducting solid sphere. Solid sphere. In this non-conducting solid sphere, okay, I want to calculate the electric field. How can I calculate the electrical field? Okay, this is the center of the solid sphere, but the charge is uniformly distributed. Okay, so that the with respect to the distance here, in this case, charge, okay, electrical field is continuously varying here. Let at a distance r, okay, I selected a small segment. This segment is obviously which is in the form of a spherical shape. So its width is, as this is r, dr I selected, so that using this Gauss law we will calculate the what is the exact amount of the total electrical field. Okay, we are around electrical field which is responsible for this uniform charged sphere. How much electrical field is produced here? So again, using this Gauss law, E here, as the charge is uniformly distributed, electrical field is uniform. Therefore, cyclic integral of, okay, E dA, which is equal to, but here Gaussian surface I selected, okay, I want to do in two ways. That's why I am using this concept. Instead, I am using only Gaussian surface, means no need to all this, right? At a distance r, I selected a Gaussian surface, right? Now E, what is the Gaussian surface area? Means surface area means 4 pi r square is equal to what is the charge enclosed here? This is a solid. As it is solid, volume charge density is equal to charge per unit volume 4/3 pi. What is the volume of this R? cubed. Therefore, I exactly how much amount of the charge enclosed in this Gaussian surface now I am able to calculate. QE is equal to rho into 4/3 pi r cubed. That I substituted here, rho 4/3 pi r cubed by epsilon naught. R square cancel, 4 pi cancel. Therefore, E is equal to rho r by 3 epsilon naught. So this is also using the Gauss law without integration method. We will calculating the how much amount of the electrical field will be there in this uniformly charged distributed body, non-conducting surface. If you draw the graph also, from this formula we know at a distance r electrical field is 0. Okay, with respect to rho is constant, epsilon naught constant. With respect to r electrical field is directly proportional to, that's why up to this surface electrical field is increases like this. Okay, outside the surface again, okay, outside the surface formula will be different. That also E is equal to rho r square by 3 epsilon naught. Formula coming outside the surface, sorry, rho, let this radius of the sphere is capital R, rho r cubed by 2 epsilon naught r square. Okay, that also after deriving we will get exactly, we know. That's why here also r constant, rho constant. Outside the surface electrical field is inversely proportional to r square. This number is, we will derive simply here also within small fraction of the time using Gauss law. E into what is the total now outside means at a outside this solid cylinder I selected a Gaussian surface here at a distance which is r, smaller, let it be again, so that this Gaussian surface is again 4 pi r square, which is equal to charge enclosed rho into 4/3 pi r cubed. This is the total charge of the solid sphere distributed by epsilon naught. 4 pi cancel. Therefore, we will get 3 here. Therefore, E is equal to rho r cubed by 3 epsilon naught r square. So, in this way, by using all this Gauss law, outside or on or inside of the solid sphere or hollow spheres or any surfaces formulas we will derive. So now using all this, now we will do some problems. Okay, let's suppose some first problem. There is a uniformly charged disk. I am considering a, sorry, not a disk, it is a sphere. Uniformly charged solid sphere. Uniformly charged solid sphere. Now I am going to cut, and its radius is and charge distributed, uniform charge means let it be q, and radius of the surface is let it be r naught. This is the solid sphere I selected. Now in the second step I am going to cut some part of this sphere. Its radius is okay, obviously r naught by 2. When I cut this, now what is the effective electrical field or what is the net electrical field, okay, which is produced by the remaining surface? That is the question. Now I am to solve this problem. Okay, first students should approach, okay, select here some reference point. Okay, I am selected here B. Let's suppose this is O, this is A, right? Now at this reference point, what is the electrical field due to the whole sphere before cut, and what is the electrical field due to the cut part. So when this as this cut part will be behaves as a cavity, there is a negative charge will be okay uh, formed here, distributed, so that the net electrical field is equal to E. Let due to whole sphere I will use it as a E1 minus due to the cut part I am used as a E2. But what is the electrical field due to whole sphere? We know KQ. What is the charge on it? Q. KQ by R naught. But in the form of rho, I am using already in the previously, this is a uniformly charged distributed body. That's why in the form of rho and R by, let it be R or R naught by 3 epsilon naught. Means here at which distance I am calculating the electrical field, at a distance r naught. That's why I am using E1 is equal to, in place of E small r I am using capital R. But what is the electrical field due to cut part? That is E2. So E2 is equal to, what is the charge on this surface? Rho, same formula, right? Here also rho into distance. What is the electrical field here? R. But what is this distance here? What is the formula? Just before we know, rho R square by, okay, means for this surface, for this cavity surface, this point is the outside now. Okay, for the whole surface, this is the on the surface, so that we got E1 here. For this cavity or this cutted part, okay, the point is outside. That's why for the outside already we know in the previously rho R cubed by 3 epsilon naught R square. Means this is a original area of that, and this is the distance of from this center to the point where we will calculate the electric field. That's why this is, I am using here one more parameter. Let it be, this is x, right? So that's why I am using here rho 3 epsilon naught x square. So ut is equal to rho into, what is r here? R naught by 2. Means r naught cubed by 8. 3 into 8 into epsilon naught into x, means what is the x distance from this point to the point where we are taken as a reference? R naught plus R naught by 2 means 3. R naught by 2 square means square. Now after simplifying this, finally we will got here, okay, this is rho R naught cubed by, here 2 square means 4, this 4 2 times cancels, right? Therefore 3 to the 6 into epsilon naught into 3 square means 9 into R naught square. So finally you will get here R naught square cancel. Rho R naught by 6 nines are 54 into epsilon naught. This is the electrical field due to the cut part. So finally E net is equal to E1 minus E2. Therefore, keeping the common terms constant, rho R naught by epsilon naught is the common, remaining are 1 by 3 minus 1 by 54. So after simplifying here, okay, rho R by epsilon naught into 17 by 54. This is the net electrical field, right, which is contributed by the remaining part after cutting the, okay, this part of the sphere. Okay, this is one example I explained, and another examples from this chapter we will understand. Let's suppose here rotatory electrostatic combination 1, and time period combination or fluid mechanics combination or from the other let's suppose I am using here, there is a large disk, on which there is a charge is uniformly distributed on the outside surfaces, hollow disk, right? And its magnitude is q and its radius is r, which is connected to a small sphere over which a negative charge will be there. If this the distance between the two centers of the space is let h, by the external force let this disk is moved through a small displacement x. Now the remaining distance, the resultant distance between them is h square plus x square over root. So this is the problem initially. Let a small disk is with the charge minus q and large disk is small sphere. Small sphere means point charge, which is not moving, not rotating also. So this is a disk charge. The disk. When this disk is rolling on the spheres, neglecting the friction, everything, pure rolling concepts here, no need to consider all. So when this disk is displaced through a small displacement with some external mean, finally let this will be moved from O to O dash, and now the distance between them is this displacement mean. Now they are asking the question, find the angular acceleration of the disk. Find the angular acceleration of the disk. So here also we will calculate. Here force concept we are using, not work energy concept or work energy theorem. Force concept means here there is a here there is a charge is plus q, here minus q. The force attraction usually here, but after displacing, because of the restoring force, means the force acting, electric force between the two charges acting at a distance in this direction, and the distance between them we know, and the two charges we know. What are the force acting between them at this position? Fe into and if this is theta, this is the force. Now this force acting in this direction means this is Fe, the line of action of the force acting here, right? And the perpendicular distance from the center to this axis of rotation. The disk is rotated from this axis of rotation. That's why the line of action of the force into perpendicular distance will cause the product of these two will produce the torque. By that torque, the disk is rotated by the external force, right? Therefore, Fe into perpendicular distance is R, which is equal to torque. Torque means what is the moment of inertia of the disk? I into alpha. So Fe means we know already in the previous case, q by direction already mentions, no need to use the sign here. Q by q by h square plus x square over root into and as theta opposite, now this one not Fe alone, Fe sin theta component. That's why this is Fe sin theta. Therefore sin theta is equal to x by that again, x by h square plus x square is equal to moment of inertia about this instantaneous axis of rotation. This is the instantaneous axis of rotation point. This point will act as an instantaneous axis of rotation. That's why about this point, what is the moment of inertia? The disk or mass is let m. Therefore mr square by 2 from the perpendicular axis theorem, mr square by 2 plus perpendicular distance is here, or therefore 3 by 2 mr square into alpha. After simplifying, then we will calculating the alpha value with the neglecting xr with x or sometimes they are asking the time period also. This is the one of the example regarding this chapter. Similarly, one more example I will explain you regarding in this chapter. Let's suppose here there are two plates will be there. This is positive plate, this is a negative plate, this is a one capacitors. Combination of the plates nothing but will behave as a capacitor. In between there is a rod is suspended from the hinge. Okay, because of the electrical field, and here again there is some electrical charge will be distributed, let it be Q. Because of the positive to negative electrical field will be spreading, right? We know in the later chapter electrostatics, that is capacitors. Between the capacitors, what are the electrical field? Sigma by epsilon naught, the sum of the sigma by 2 epsilon naught plus sigma by 2 epsilon naught is equal to, finally we will get the total electrical field of this combination of the plates is sigma by epsilon naught. And in this electrical field, if this charged rod is suspended, there is a force acting on it. Because of the electrostatic force acting on it, the rod is displaced through the displacement theta, right? Okay, now the force acting on this rod, first we will calculate. Fe is equal to E into Q. Fe is equal to EQ, all of you know this. According to this one, sigma by epsilon naught into Q. This is the electric force acting on this rod. Now at some intermediate position theta, that is we assumed at this instantaneous angular position and at the equilibrium angular position, okay, what are the forces acting on it? Finally, what are the questions asking in this one? In this demonstration, they are asking what is the angular velocity or what is the angular acceleration. These two questions mostly they are asking, or sometimes okay display here, these two only mostly possible, right? Now to calculate the omega or to calculate the alpha, we will use the force concept. Force concept. What is the force concept? What are the force acting here? The force acting at the center of mass of this body. Okay, therefore this is the force acting. What is the force acting here? This is L by 2. The resistance is L by 2. Hypotenuse we know, theta we know, opposite. This is only horizontal force only acting. Okay, that's why force into perpendicular distance, L by 2, force into perpendicular distance. That's why this, by the definition of the torque, force into perpendicular distance is equal to I alpha, right? So force means we know sigma by epsilon naught into Q into L by 2 is equal to, what is the moment of inertia of this rod about this one end when it is inclined through the angle theta? We know that formula also, m L square by 3 into alpha. This also by deriving we will get it. From this one we will calculate the alpha value. Okay, by the force method. If they are asking angular velocity, okay, what are the concept we will approach to calculate that? Mean here energy conservation or energy concept. Energy concept. So according to this energy concept, what is the energy here? Energy means here work has to be done. Work will be converted into different forms of the energy. But work is here force into displacement. What is the force here? Fe. What is the displacement here? L by 2 sin theta. Hypotenuse we know, theta opposite. L by 2 sin theta. This is also force into displacement, but this is along the direction of the force displacement, which is responsible for the work will be done. This work is converted into here rotational kinetic energy. That rotational kinetic energy is half I omega square. So potential energy does not changes here, only rotational kinetic energy only we will calculate. Why? Because position of the center of mass does not, okay, even though changes, potential energy is neglected here. So Fe means we know again calculated here, sigma by epsilon naught into q into L by 2 into sin theta is equal to half into m L square by 3 into omega square. From this one we will calculate omega, and also if we want time period also. So this is the third examples from this chapter. Okay. Next, from the fluid mechanics, one more problems I will explain. After that, I will end this demo from this electrostatics. That also from fluid dynamics, all of the students very familiar. When a body is immersed in a fluid, how much force acting on it upwards? Okay, equivalent to the volume of the body immersed, that equivalent volume of the water will act the force on the immersed body upwards. That is called buoyancy force. Buoyancy force means, okay, that whole body is immersed means total mass of the body into g. Okay, but what is the mass of the body here? How much total mass of the body means mass of the body mg, force is equal to mg. Okay. Oh, or this is the gravitational force we are speaking. But what is the buoyancy force acting? Buoyancy force acting means here we will not mass is equal to volume into density. Mass is equal to volume of the body immersed into density of the body liquid. Okay, which is responsible for the force acting upwards on the immersed body. Right. Using this concept again, we will use some. How can we find the dielectric constant? Dielectric constant of the medium in which the simple pendulums are immersed. By this method, we will find the dielectric constant of the immersed dielectric constant of the medium in which these two spheres are suspended. But here also there are two cases. Without medium, when these two spheres are suspended, two identical spheres of charges are q and q are separated at a distance r, and angle between them is theta, right? But here there is an important point the students should understand in this question is, even in the air or even in the medium, theta is not changes. Theta is not changes. This is the important point observed in this lesson, right? So first, in case 1, right? In case 1, when spheres are in air, what are the forces acting on it? Let a force acting vertically downwards, mg, without medium we are speaking. Let the tension build up in this wire is T. So if this is theta, this is let theta, this also theta. So this is also theta, this is T cos theta, and horizontally T sin theta. Here T cos theta balanced by mg, T sin theta balanced by electrostatic force between the two spheres. Therefore T sin theta is equal to force by force. Similarly, T cos theta is equal to what is mg. Okay, after defining, we will get here tan theta is equal to Fe by mg, equation 1. When we immerse this whole system in the medium of any liquid also, theta does not changes, but what are the factors changes here? Only T sin theta is equal to Fe dash, let it be here, force will be changes. Okay, but what is T cos theta? In the case 2, addition of this T cos theta, there is a buoyancy force acting upwards. Therefore, T cos theta is equal to mg minus Fb. Here we are using mg minus buoyancy force. That's it. After dividing again, he same tan theta is equal to Fe dash by mg minus Fb. Equation 2. From this 1 and 2 equations, as LHS is same, we can equate RHS. From RHS again, Fe by mg is equal to Fe dash by mg minus Fb. Take Fe dash here. Fe by Fe dash is equal to mg by mg minus Fb. But we know from the force concept, F is equal to 1 by 4 pi epsilon naught charge Q1 Q2 by R square. Q1 Q2 by R square. So here force is inversely proportional to epsilon naught. That's why when they are in air, okay, when they are in medium, force ratios are inversely proportional to the permittivities. Therefore, we can write it as inversely proportional means medium by, okay, permittivity of the medium by permittivity of the, okay, as this force is in air, but here medium coming. This is in medium, this is in air coming. That's why permittivity of the medium by permittivity of the, okay, permittivity of free space, which is called dielectric constant, which is equal to, after dividing this whole by mg, we will get 1 by mg again cancel 1 minus, but Fb means already Fb calculated here, V rho L G, V rho L G by mg means mass means volume into density of the body into G. V cancel, G cancel. Finally, dielectric constant is equal to 1 by 1 minus rho L by B or rho B by rho B minus rho L. So, in this way, we will calculating the dielectric constant of any medium. Okay, by this method we will find. Like this, many examples we will solve across this electrostatics chapters. Right? Thank you.